Okay, hi everyone. I'm going to start. So today I've decided to spend some time explaining to you in more detail how to use TINA one-zone computational tools, because a week ago, because of the lack of time, I wrapped it up quickly, but this is important. This is an important part, because most of you will probably be using TINA computational tools because they allow to reach various goals, actually. Right. So now I'm going to start sharing my screen and to show you step by step how to use TINA computational tools. Okay. Okay. So this is the Astra Hub gateway page, which is already familiar to you. Excuse me. So let me go to TINA. So this orange square. When I click it, I'm not going to do this because I've already done this before today's lecture. When I click this, there will be another screen where we will have to click the orange line named spawn. Okay, after that, you will find yourself here in this Jupyter Python notebook, right? Okay, so first of all, you can click here in the left bottom lower corner, the window terminal. Yeah, you can do this. In this case, I see. So in this case, you will see that this window will become just Linux, like a Linux computer window. So here you can execute different Linux commands. For instance, just ls command, which lists all files and directories available here. So you can see there are actually one directory, this directory, and these are two links. And these three files are also, as you can see them here in the left margin. So you can either work with this left margin, clicking with your mouse, so different files and directories here, or you can work also from time to time in this Linux window. Okay, so when you are here in TINA, the first thing, of course, wherever you are, the first thing, of course, is to find and have a look at README file, like, right? For instance, here at the very beginning, there is, this is the main TINA, TINA's main README file. So to open it in a viewing browser, first you highlight it, then you click the right button of the mouse, right button. Then a window opens which allows you to choose how you want to open this README file. If I clicked editor, then it would be editor window, which I don't want. I'm not going to edit this file, so therefore you should choose, after clicking here the red button, open with markdown preview, right? Then you will see here on your screen this short text, which gives some information about TINA, what TINA is. TINA stands for Training in Nuclear Astrophysics. Welcome to the TINA Hub, etc., etc. You can read this later. There are some links here. You can also click these links if you are interested. Okay, but the most important thing is in this second paragraph, which says to get started working with TINA, first select the directory network school in the file manager. So file manager is this left margin. So it says that we should select this network school directory. But let's finish the reading. So if you are a new user, create a new iProcess run directory using the make new iProcess user directory Python notebook. Read carefully. You will have to edit one cell at the beginning of the notebook. I will show you this notebook. So this paragraph actually says that we should go to this directory, network school directory. To go there, as you know, to go to directory, I have to double click it with left button, double click. So now I'm in this directory. And in this directory, as you can see, there are directories with different names, students' names, including my name here, Pavel, that I created before today's lecture, excuse me. But as this text here in the README file says, on the next step, you're supposed to use this Python notebook, make new iProcess user directory. It's here, as you can see. It's here, make new iProcess user directory. So in order to open this notebook, you have to click it again twice by left button. So then it will open here in the top bench of your window. I've already done this before, so therefore I go here. So okay, I can close it here by clicking with left button cross. Okay. And then I go again to network school, clicking it 2 times, okay, and I open it again, okay, open it again. So in this main notebook, make new iProcess directory, what you can do if you have not done this yet, you can create here in this network school directory, you can create a copy. You can create your own directory with your name, okay? And this directory will be filled with all TINA computational tools automatically. So for this, you are going to use this notebook, make a new iProcess directory. You can read, there is some information here. But the important thing, you provide here in the first cell, the name of your directory. You can see here I have chosen my name, Pavel, and as a result of my using this notebook, this directory here on the left, in this file manager, you can see it with name Pavel, was created. So therefore, I'm not going to do this. You will choose here whatever name you want, okay, your name. Then in the second cell, yeah, I hope you know how to execute cells. Of course, to execute a cell, you just click simultaneously Shift and Enter. Okay, next cell, step 2, it will check first if there is already here a directory with your selected name. Because there is directory with name Pavel, I'm not going to do this, execute this cell. And finally, yeah, step 3 is important step as well as other steps, of course. On step 3, as this comment explains, when you execute this cell on step 3, this is where this notebook actually will clone TINA computational tools in your directory. As you can see, git clone. This is the path to the repository, GitHub repository with TINA computational tools. And this repository will be cloned, as you can see, to the new directory with your provided name. So in my case, into the directory Pavel. Okay. Then next, step 4 in this notebook, you execute all steps, of course, step by step, unless you have already done this. Okay. Next step is also important because it makes links, aliases, links to directories that are important for successful execution of one's own NuGrid code. So just execute this file. Link to this file, NP data, will be provided. By the way, this directory, NP data, contains information about files about nuclear reactions used by NuGrid one zone, both one zone and multi-zone codes. And the second link is just refers to the so-called directory master results, where there are some results for you to compare, some test results. But this is not that important, okay? But you execute all the cells. Finally, on step 5, as this text explains, on step 5, you just check, you test if everything is okay. If I process one zone NuGrid code, which is in directory your provided name, then subdirectory I process, and the code's name is ppn.exe. This last cell will just check if everything was done before correctly, and the code can now be run in your directory. Okay, so I have done this before the lecture. So therefore, now I go to my directory. So for this, after you will execute this cell, which will create here on the left directory with your name, you will see that a new directory will appear here with your name. Don't forget to execute the rest of the cells, because they will populate your directory with all necessary data. So as I said, I have done this already. So therefore, here on the left, as you can see, now I go to my directory with name Pavel. So I highlight it and I click, double click it with left button, double click. And now you can see, you will see the same directory structure in the directory with your name. Okay. So as I explained before, TINA computational tools now so far allow to do computations for 4 nuclear synthesis processes. This is I process, this subdirectory I process. This is NOVA, one zone nuclear synthesis computations, X-ray bursts, and co-collapse supernova, CCSN, right? Okay. So now I'm going to use as a demonstration for you calculations for I process. Okay. So therefore, I go to subdirectory with name I process. Again, double click with left button of the mouse. Okay, so each of these directories, I process, NOVA, co-collapse, supernova, and X-ray burst, XRB, they contain some files. Okay, when you enter one of these directories, for instance, I've just entered the subdirectory I process. First, have a look at the notebooks. There are 3 main notebooks in each directory. Notebooks actually can be recognized with this orange symbol. These are notebooks. So each directory contains 3 main notebooks. They are called, let me just move this to the right. They are called Model Runner notebook, okay, Result Explorer notebook, and Rate Changer notebook. Okay, I've already to open them, of course, highlight them and double click with the left button. I have already done this. So therefore, after that, after you will open them, click, their names will appear here at the in the top band, and then you can just choose them. For instance, this is my I process model run notebook. Okay, and yeah, so one thing to keep in mind, okay, please remember this. So model runner notebook is probably for the first time use all 3 simple notebooks. Model runner notebook is probably the notebook that you will be using more frequently, this model runner. So it's open here because it allows you to run your nuclear synthesis one zone computations, in this case for I process. This Result Explorer notebook, it allows to do a very simple analysis of computational results that you obtained with Model Runner notebook. But these notebooks, Result Explorer notebooks in each directory, they were developed initially for high school students. So therefore, my point is that they are quite simple for research. Okay, you can still use them just to learn how, in principle, to use TINA computational tools, right? These three notebooks, Model Runner, you will be using it more frequently, as I said, then Result Explorer, which does some very simple analysis of results obtained with Model Runner, and Rate Changer. You can read about these notebooks in provided text here, so I'm not going to go in more details about them. But what I'm going to tell you, because you are not high school students, but you are graduate students, you will probably want to use the other more complex notebooks, which are located in each subdirectory in the subdirectory notebooks here. Okay, so let me double click with the left button the subdirectory notebooks here. Okay. Yeah, can you hear me? Am I not muted? No.
No, you're good. We can hear you.
Okay, because so thank you, because I forgot if I unmuted my mic. Thank you. Yeah, so when you go to subdirectory notebooks, which exists in each nuclear synthesis process subdirectory, then you can see here there are more notebooks. And these notebooks in the subdirectory notebooks, they are for advanced users like you, like gradient students, right? And you can see this green circle to the left from each of these three notebooks. It just says that I have already opened these three notebooks. They are here. You can see for iProcess, for instance, this is neutron density and exposure notebook. It's open here, this thing here. Elemental abundance notebook, it's open here. And abundance and flux chart notebook, it's open here. So therefore, I'm not going to click them because these green circles, they just say that they are already opened, okay? So therefore, if I'm interested in studying, in calculating iProcess nuclear synthesis and analyzing results of my calculations, right? Then I go, of course, to iProcess subdirectory. I start notebook model run here. This is model run, which is open here, right? Yeah. And first, of course, I have to do computations. One zone nuclear synthesis computations of iProcess. Let me use this notebook, model runner notebook. Therefore, I said that you would probably use it more frequently than other notebooks because you can do computations with some changes introduced, say, in your reaction rates, for instance. So therefore, this notebook will be used more frequently. Okay, you can read the instructions here. I'm just going to skip them so that we don't lose time. And I go to the first cell, and you can see the first cell will already execute one zone nucleate PPN code. Okay, so before we will start these computations, right, we have to be sure that we will do computations in which we're interested in, right? What I mean. So I go back to subdirectory iProcess here, where there are quite a lot of files, and all computations are done in this directory. Okay, and I need to tell you that you probably want to change some input parameters before you start the computations in this notebook, right? In most cases, you will probably want to change parameters in the input file for these computations, which is called here on the left in this file manager. It's called PPN, as the name of the code here, PPN underscore frame.input. Input means input file. In order to check what default parameters are, you again open this file ppm frame input. To open it, you just double click it with left button. I'm not going to do this because this file here is already open here. So I just click and this is the content of this file. You can see when I click it in the upper band, when I clicked it, the file in the file manager became highlighted with blue. This means that this file is now opened on my screen here. Okay, so these are input data for PPN code, and probably you will be interested, not probably, but I recommend you to be interested only in the following two things. Okay, the first thing you can see PPN frame. It explains here there are three iProcess nuclear synthesis cases here, right? First, case 1 corresponds to second peak for CMPI stars, right? This is second peak for CMPI stars. Yeah, and by the way, I said that before, but that didn't show you. I said that each subdirectory should contain some README file, and therefore you should start, of course, with opening and reading README file. So let me go back by one step and find README file. This is README file in the subdirectory iProcess. So I highlight it and I click right button and I go open with, and I open this README file with markdown preview, not with editor. Okay, and this README file explains the differences between these three iProcess nuclear synthesis cases, right? No, it doesn't, of course, explain this in detail. It just provides links to corresponding publications. So therefore, if you are interested, before starting calculations, you can click these links and have a look at the corresponding papers to understand what these iProcess cases mean. Second peak for CMPI stars or CMPI stars. Sakurai case, this is for iProcess nuclear synthesis in Sakurai's object, okay? And weak iProcess, this is, we think this is iProcess nuclear synthesis responsible for abundance anomalies in this metal poor star HD 94028. So therefore, before you start doing anything in each subdirectory, first, of course, please read README file, okay? Yeah. So now, after I have read the README file, I go back to model runner directory. Okay, and again, before starting the run, I check the content of ppn frame.input file, right? First of all, as I said, you can choose here iProcess nuclear synthesis case. So you can see this exclamation sign, right, in front of a parameter name and its value. Exclamation sign means that this information is commented. It won't be used by execution code. It won't be used in computations, because exclamation sign means its information is commented, right? You can see on the left there are exclamation signs with text. This means these are just comments, and you can see that only case 1 here is uncommented, right? This means that if I leave this file as it is right now and start computations in model runner notebook, then case 1 will be computed. If I want to change the case, say to Sakurai object or to weak iProcess, I should first comment case 1, like putting exclamation sign, and uncomment here, say Sakurai object, okay? So now I'm going to use case 1, so therefore I again comment Sakurai case, and I uncomment case 1, which is second peak case, right? Yeah. When you do these changes, you should save the file, right? Your changes. To save them, you go here to the left top. You can see a file. You click left button file, and here save file. So now this information is saved. So this is the first thing that you may want to change in the ppn frame.input file for iProcess nuclear synthesis computations. The second thing that you may want to change, okay, is this parameter. iplot_flux option. By default, usually this is already changed that I made before today's lecture. By default, it has here value 0, iplot flux option 0. And this comment behind the exclamation sign explains that when the value of this parameter is 0, there will be no printed fluxes. What reaction fluxes are, I will show you in later in a few minutes. So the difference with using a value for iplot flux option 0 or 1, the technical difference is that if I use 1 instead of 0, first of all, computations will take a bit longer time. If the value is 0, these computations will take, I would say, maybe a couple of minutes. If I will change this value from 0 to 1, computations will probably take 5 minutes, 8 minutes. So the difference is not huge. But what's more important, if I use the value for this parameter 1 instead of 0, then there will be more output files. Besides abundance, isotopic abundance files, the computations will also output the so-called reaction fluxes files. And unfortunately, those reaction fluxes files, they are quite huge, you can see, you can check that if I use here 1, then the volume of these fluxes files will be a few gigabytes, okay? So therefore, you should use here the value 1 only if it's actually necessary, right? Yeah. By the way, before today's lecture, I already made the run for case 1 for second peak with flux option 1, so that we'll not spend time during lecture, and I will show you results. But the default value is 0, so therefore I'm going to leave here a value 0 so far, so that I will not forget to change the 0 later. Okay, now I go back after I introduced these changes, after I have selected iProcess nucleosynthesis case here and decided if I need fluxes or not. Okay, I go to model runner and I start computations here by executing this cell. Okay. So let me try this. So remember now, when I start this computations, executing this cell, I will be computing iProcess one zone iProcess nucleosynthesis case 1 that corresponds to second peak CMP iStars. There is a link reference to the paper that you can have a look at. Okay, and I will be not printing out fluxes, right? So let me start the execution of this cell. Shift enter, right? Shift enter. You should see something like this. This is computation started. Okay, now you can see some output. While computations are going on, you will see here in the right top, the circle will be black. You have to wait until it will become white, which means computations are done. Also, as computations go on, this is, I just scroll the screen with the wheel in my mouse. I scroll the screen, you can see computations continue. You can see on the left, in the file manager, that new files appear. These files, first of all, iso_massf, etc. So these are files with isotopic abundances. And the number of the file 0, 1, 2, 3, 4, 5, etc. They correspond to time step of these calculations. You can see also on the screen 458. This is the time step. Okay, time step is chosen automatically. You shouldn't care about it. You should trust the code. And you can see when I scroll file manager on the left down, you can see now there are quite a lot of this isotopic abundance output files. Okay, now 758. Now I scroll the screen. For case 1, iProcess nucleosynthesis will be in total 891 time steps. You can see the last time step here on the screen is now 891. And now this circle here on the top right is white, which means calculations have finished, right? And on the left in the file manager, I see that the last file with abundances computed was at time step 891. So in new grid community, we often usually call time steps cycles. So therefore, if you hear from new grid members what's cycle is just time step. So 891 times that 891st time step means cycle number 891. So don't be surprised if you hear cycle number. This is just the time step. In the file manager on the left, you can see that there are in the output only this isotopic mass fraction. This is iso-mass-F, means isotopic mass fractions. This is mass fraction of isotopic mass fractions, right? For instance, if I open one of these files, again, double clicking with the left button, okay, I can see its content here on the screen. You can see it says here also model number 891. So these are all synonyms. Model number, cycle, and time step. All are synonyms. A model 891. Age in years. Age it still traces back historically to the time when the code was developed by Falk. And because Falk is German, you can see here, you see HJ. J is Jahre for in German, years in German. So therefore, don't be surprised. Similarly, die Zeit. Zeit is German for time. Okay, and D means delta. So this is delta T. So this is time step. Okay, everything here is given in years. So therefore, you can see for this model we had time step d Zeit delta T equal 7 times 10 to the minus 5 of years, because in the year we have three times 10 to the 7 seconds. This means it's like few hundreds of seconds. And H here is 7 times 10 to the minus 3 years. So this is less than 1 day for calculations. Okay, yeah, and below this header information below this, you can see a long detailed list of isotopic abundances. For instance, this is carbon 12. It has the order number 11 in this list, from 1 to 11. 6 is obviously the proton number for carbon. 12 is atomic mass for carbon 12, right? And this is its mass fraction obtained for this time step 891. This is its mass fraction. So it's approximately 0.036. Okay, so this is content of all this isotopic mass fractions files. I'm going here to close it by clicking cross. I closed it. Okay, if I ran it these computations with flux parameter equal 1, then additionally to iso mass fraction files, I would also gotten my output files with name flux. So I can show them because I have stored them before today's lecture in a directory. Here, run second peak. This is, you can see, 2 hours ago. I did this run before so that we don't spend time during the lecture. Let me just double click it. Okay, so you can see that along with iso mass fractions files, like I've just shown you in the parent directory here, there are also files, output files with names flux. So this number is again cycle or time step, but these are huge files. So this is content of this file. I'm not going to explain you what's inside these files. This is information about reaction fluxes, which actually show for each reaction what's its importance for a given nucleosynthesis. Yeah, I will show you this later in a plot. So I go back to iProcess subdirectory, okay? And now back to model runner notebook. We've just finished the run, okay? Now the next cell just checks that output files are in the current directory, ls I'm not going to execute it. The next cell is important. This is where you save results of your run in a directory with your provided name. You can see this is from leftover from my computations 2 hours ago. I saved results of my run with fluxes, reaction fluxes in the output in the directory with name run_second_peak that I've just showed you. You can choose here any name for a directory where you save the files. Just remember this name because this name will be used in the analysis notebooks, okay? That's it. So model runner notebook just executes computations, okay, with whatever parameter values you used, and saves the results in a directory with your provided name, okay? So now we could go to those simple analysis notebooks and you can try them. Okay, so let me save results of my computations in a directory so that they are not shown in the file manager on the left. So to not add them to my existing directory here, I will change the name of directory. No flux, no flux, right? Yeah, like this. So now I execute this. Okay. Just a second. Process. Yeah. Okay. And now I check if everything was copied to the directory with new name. No flux. Yeah, everything is there. Okay. So now you can see on the left in the file manager, now I have 2 directories with result. One run second peak with both abundances and fluxes in the output, and the second directory with name run second peak no flux, where I saved results without fluxes, okay? So you can make here as many output directories as you wish, and later in analysis notebook, you can compare results of different computations with changed input parameters, right? It's up to you. So now, as I said, each of one-zone nucleosynthesis subdirectories, in this case iProcess, has these 3 notebooks, which were developed for high school students, so therefore they do only a very simple analysis. Now, in order to do more interesting analysis that corresponds to real science, more or less real science, to research, as I said, I use notebooks from the subdirectory notebooks, these 3 notebooks. You can see green circles means that I already opened, so therefore I'm going to close this file manager on the left, so it doesn't abstract the look at the notebooks. To close it, you just click this black thing here. So you see it's closed, then you click it again, it's open, closed, open, okay. So I close it, now I have the screen for my analysis notebooks. First, I go to neutron density and exposure notebooks. Remember, I'm going to use 3 notebooks from hidden in the subdirectory notebooks, which are designed for advanced users like you, okay? Okay, so now in this notebook, neutron density and exposure, this notebook allows you to make a plot of neutron density and exposure, of course, as a function of time for your computations. So these notebooks for advanced users, they already set up for the 3 cases that I mentioned before, iProcess cases, case second peaks, case Sakurai, and weak. By setup, I mean that when you make a plot, right, you want the plot to look as good as possible, which means you have to tune up some arguments in the function that makes the plot so that the plot looks good. Okay, so for you to save time in these notebooks here, we already did such tuning up of parameters for plotting, and therefore you have to only pick up the corresponding case, and then you will see that for the corresponding case, notebooks will choose the corresponding tuning up parameter. Because now I've just done computations for the case, I processed nucleotides case second peak. You can see here I uncommented the name of the parameter case second peak. In notebooks, comments are provided with this symbol, okay? Okay, now I commented it. Now I uncommented it. Okay, so now you can see I have chosen case equal second peak. Let's execute cell by cell by clicking Shift and Enter. Okay, initializing the notebook. The cell just reads necessary Python scripts. Okay. Okay. So now here we take some physical constants. Okay, you can see Avogadro number, Boltzmann constant, etc. Again, now next cell again, case name. This is not necessary to provide here if it's already was provided in the first cell, but it's still here. But what's important, look, the second parameter is the name of the directory where you saved the results, right? You can see here run dir, the name of directory is my directory run second peak, where I saved before today's lecture both fluxes and abundances. So I'm going to use them. So for you, I did computations without fluxes and output, but before I saved fluxes in this directory and abundance. So I'm going to use this directory, okay, which is of course here, this directory, not this one, okay. Okay, so now I close this again. Yeah, so I choose this directory. This is just assigning names, okay. And now next cell will read data from the run directory. In this case, yeah, some data, okay. Okay, we have to wait until this black circle becomes white. It's white, which means reading is over, it's finished. And you can see as a result, it says that the number of species that were included in our nucleosynthesis computations was 5,214. So all this one zone, TINA one zone nucleosynthesis computations are done with the full list of isotopes available in NuGrid codes. It's 5,214, which guarantees that you will not miss any species. Okay. Okay, and the last string here says that there were 891 time steps, right? Yeah, we know this already. You should keep this number in mind because in principle, when you do some other computations, because this is the maximum number of cycle or maximum number of the time step that you can use in plotting cells, right? If you provide in a plotting cell different number like 1000, that will report an error. So I cannot find, of course, this file, obviously. So now this cell prepares some quantities to plot. Remember, this notebook will plot neutron number density and exposure as function of time. So prepare some quantities. Now we will make separately neutron density plot and neutron exposure plot. And after that, combined neutron exposure and neutron plot. Okay. So this is neutron density plot. Okay. Next cell, neutron exposure plot. And the final cell makes the plots both neutron exposure and neutron density here. Okay. Yeah. So let's have a look at this final plot. So the horizontal lines gives time in minutes. Okay. So right, starting from 0, of course. and computations were finished here, and that was the choice of parameter for case 1, for second peak case. Computations were finished at approximately this time. Yeah, it's approximately 3,720 minutes. So the blue curve, there should be a legend here. Just a second. Where there is no legend. There is legend. I just didn't see it. Okay, so you can see this. These are the legends. So the blue curve gives neutron density, capital N sub n. This is the number of newtons in cubic centimeter, and you can see it is shown on the left vertical axis, neutron density in per cubic centimeter, and it's shown with blue line as a function of time. You can see in this computation neutron density quickly reaches some maximum value around 10 to the 16, and then it gradually decreases. Okay. So the orange dashed curve gives tau, and tau is the neutron exposure. Okay. This is actually a neutron density multiplied by thermal velocity of neutrons integrated over the time. Okay. And neutron exposure is its values are given on the right axis. It's usually measured in millibarn, in reverse millibarns. And the orange curve here shows the neutron exposure. You can see the maximum neutron exposure reached in these computations is approximately 20. It's approximately 20. Okay. So that was this first notebook. Now let's go to more fun notebooks, elemental abundances and abundances. So let's go first to this notebook, which is called Abundance and Flux Charts. As the name of the notebook says, here we're going to make plots of abundances and reaction fluxes, right? So you will see how reaction fluxes look. Again, the first cell selects the case. We still have case second peak, so therefore execute this cell, shift enter. Okay, and now initializing notebook. The third cell again, case name, and the directory where we save the results. It's name run second peak, but you can choose some other name. It's up to you. Okay, now we reach output data here. Results. It takes some time. Okay, we have read them. Now the next cell, as this title says, will make a copy of the file flux cycle to plot that in the notebook's directory. Because this is necessary to do, but this cell will do this for you automatically, because the output flux file must be present in the same directory from where your current notebook is taken. Okay, this is what's historically done. So therefore, as you can see in this cell, we select the case in our that will be case second peak, and for the corresponding case we select the maximum number of cycles or time steps. Okay, of course you can do this yourself, but this is done so that you don't care. So, and the file with cycle number 891 for flux will be copied in the directory where this notebook is. This is what this cell does. Okay, so it's copied. Now we clean space for plots, close previous plots if they were open, and now we're going to make some plots. First, make a plot of chart of reaction fluxes. This is what I was talking about. Again, you can see here, this cell just selects between three cases. It will select second peak case. And there are, as I explained to you before, you can see here some input arguments in this script, ABO flux chart script. And this arguments, you can see they have here different values that were adjusted so that the plot for the corresponding case looks nice, okay? But you can play with these parameters, you can change these arguments and see how this will affect the plot. Okay, so now execute this cell, it takes some time. You can see the black circle, you just wait until it will become white. It usually takes not more than 1 minute. Okay. That's not, it's not done yet. You can see it's still black. Let's wait. Yeah, now it's white. It's white, and these are the plots. Okay, so there are two panels in this plot. The upper panel with these green boxes, it shows, as you can see here, the color bar shows decimal logarithm of mass fraction. X is the mass fraction of the corresponding species isotope, with different degree of green, or green, yellow, etc. So the horizontal axis provides neutron number, vertical axis proton number. So this is like a chart of nuclides, neutron number from left to the right, proton number from bottom to top. And these numbers here, they provide the corresponding atomic number, which is just the sum of neutron number and proton number. For instance, 75 plus 60 gives 135, this atomic number. So solid boxes correspond to stable isotopes. All other boxes correspond to unstable isotopes. So this red line corresponds to magic neutron number, because it's neutron number 82. So this magic neutron number 82. As you can see, because magic neutron number works as a bottleneck, you have accumulation of isotopes close to this magic neutron number. This is the region of barium. Barium has proton number 56. So this are barium isotopes. And you can see to the right, from the value of stability, all these isotopes are unstable. So this plot shows undecayed abundances caught during their production at the time step equal 891. They are not decayed because if we let, in principle, we can allow them to decay, which means that after sufficiently long time, they will all, unstable species will all decay along isobars diagonally to the left and top in this direction. So this 142 and this 142 will decay into this stable 142, etc. But these are shown, this plot is shown for undecayed abundances. So the top panel is for mass fractions. The bottom panel shows reaction rate fluxes, a decimal logarithm of F, and F is a reaction rate fluxes. It's determined in our paper on Sakurai's object. I showed you the link, you can have a look. But reaction rate flux actually shows the strength of the corresponding reaction, as you can see with color. The yellower the color, the stronger the reaction, okay? And you can see reactions here are shown with arrows. And we can find the strongest reaction have the, for instance, these are the strongest reactions here, okay? These reactions which become red and thinner arrows, these are slower reactions, okay? Yeah. So now let's continue. Finally, in this notebook, which plots abundance and flux charts, finally we make a plot of charts of isotopic abundances that we obtained in these computations. I process nucleosynthesis, case one, second peak. Again, let's wait until this black circle will become white. It's still black, so it's not finished yet, so let's wait. Yeah, now it's finished. So you can see we have two isotopic abundance chart plots. Okay, there are two because they correspond to different proton numbers. You can see in the top panel, proton number goes from around 40 to 70. In the bottom, it goes from around 70 to 85. Okay, let me check. Let me show you this bottom plot. So it shows here with this color, with the color, according to this color bar, it shows decimal logarithm of mass fractions x. All right, red corresponds to approximately mass fraction 10 to the minus 4, which is quite high for this heavy elements. And this bottom plot actually shows the end points of I process and S process, which occurs around bismuth to 8 and lead. So this is actually the end point of I process. Okay. Yeah. And as you can see, different colors show the most abundant here element, by the way, this red thing. 210. That's probably polonium to 210. I don't know. Let's see, it's proton number 82. No, that's not polonium.
Lead?
I don't remember. Okay, let's not discuss it right now. But you can see the color just corresponds to a mass fraction. No, proton number 82. Lead, probably lead. Yeah, thank you. Okay, so I showed you, demonstrated you how to use this plot from the subdirectory notebooks for advanced user, right? Now the final notebook from this subdirectory, which is called Elemental Abundance Distribution and Comparison with Observations, right? This is the fun thing to compare results of our computations with observational data, right? Okay, so again, the first cell just selects the case. Again, case second peak, let's just execute it. Then we initialize the notebook, we fill with necessary functions, etc. All right. Now you can see the next third cell here makes a big selection for 3 I-process nucleosynthesis cases. For instance, let's have a look at our case second peak. What does it select? It selects first the number of the cycle to plot. In this case, we selected 830. It will be clear later why we have selected not the final cycle. Remember, the final cycle was 891. It will be clear later why we have selected here 830, close to the last one. Then the next thing, we select ppn dilute, this small number. The comment here explains what it is. This parameter adjusts dilution coefficient for the last plot. You probably heard about that already, or if not, the abundances that we have just calculated, right? They are not directly seen at the surface of, say, CMP RS star. What we see at the surface of a CMP RS star is a mixture of this, of our calculated abundances with abundances that represent initial chemical composition. Because this I process doesn't take place in CMP RS or CMP I stars. CMP I stars are just polluted by products of I process nucleosynthesis that occurred in a star of the previous generation in the past, right? So therefore, we need to take into account dilution, and dilution coefficients in this case, it's small. This means this is amount of our calculated I process abundances, the fraction of them, that we want to add to initial chemical composition, which is usually solar scaled abundances, to reproduce the observed chemical composition of a CMPI star. So sometimes dilution coefficient is 1 minus this, okay? We have chosen just a small fraction of I process abundances that we are going to add to initial chemical composition. You can see this is really a very small amount of I-process abundance that we're going to add to initial chemical composition. If I multiply this by 100, this is less than 1%. This is 0.25%, right? So the next parameter is just the case. Observed elemental abundances are supposed to be in file star. Okay, this is the name of the star with which we are going to compare our calculated predicted abundances. That pin 57 is atomic number, this proton number of the element used to pin abundance distribution profile. I will explain you later what pinning means. Selected cycles for a comparison. You can see here we take into account the last cycle. This cycle is in the middle. Okay, let's execute this cell, which will pick up parameters adjusted for our case second peak. Now, again, don't forget here to choose the right name of the directory where you save the results. This is my directory. Okay, now let's read the output data. Okay. Okay, now the first, I will encourage you to practice with this work that I'm explaining to you right now during the next week, okay? Because there is quite a lot of information here written in comments that I'm not reading just to save time, but you please read all the comments, right? Try to understand them. By the way, this is a useful cell. You can see this comment is commented here, right? But if I uncomment it and execute this cell, what comment is executed here? So PA here is just the name of data that we have just read, and it's called instance, the data instance. Okay, so PA, this is the name. I called the output data that I've just read in the previous cell, right? So this instance of output data point means apply this function after the whose name is after the point to this data instance, right? And the name of the function here is elemental underscore abund, and this is the name of one of many functions that were developed by new graders to make good analysis plots, right? And this cell, which was commented like this, so that it's not necessary to be executed each time, but now I'm going to execute it. Look, anytime you have some questions about what this function, elemental, in this case, elemental underscore abund, what this function will do with this, will do or can do with this output data. And then you put the name of this function with question mark and execute this cell. And you will see that execution of such cell with question mark in the name of function will give you explanation of what parameters, what arguments can be used in these functions. You can see the first argument, the cycle. This is just the number of the cycle you want to plot. Then the range of proton number from, and the values which are given here after the question mark are default values. So they will be used if you will not provide any arguments, right? But you have at least to provide the cycle number, probably, yeah. But you can change, of course, these numbers by providing in parentheses your numbers, okay, etc. So, and you can do this for any comment with question mark, just to have a look at the and later it explains what this actually function does. So this you can see quite a long output here. So therefore, it's actually commented here, so that if you don't need, you just don't execute it like this, okay? And now this is a function that I said elemental abund, and all NuGrid functions, they can be actually found in the NuGrid website. So if I go here, this is newgridstars.org website, which is mentioned in all documents, newgridstars.org. And here, if you go to codes facilities, clean, and then you select NuGrid Pi Python tools to analyze NuGrid data. This is where some description of different functions that are used in plotting NuGrid plotting notebooks are explained. If you go here, and then you go to documentation, it explains. Okay. Here you will probably need for one-zone calculations this NuGrid Pi PPN. PPN, this functions relevant for one-zone calculations. If I click PPN, you can see abo vector. This is a function that I've already used in one of these notebooks. Xtime I also used it. So here you can get some additional information. So therefore I report this for you. Now I'm back to this third and last notebook. And now next cell just uses this elemental abundance function to make some abundance plot. You can see there are two calls of this function. The first one with cycle number 0. This is from where we start our computations. And then the second call, the cycle number is PPN cycle, which is 830, was adjusted before. So therefore, they will compare. They will make these two plots. They will plot two curves in the same plot because the figure number 1 is the same for both plots. You can add here more calls to the functions if you want to, for instance, compare different cycles. If I execute this, execution of this functions takes usually no longer than 1 minute. You just have to wait. Okay, you see, now we have a plot. As a function of proton number z, all right, decimal logarithm, all logarithm are usually decimal, not natural. Logarithm decimal of mass fraction. There are names of elements here because we have proton number. These are elements, not isotopes. And by the way, when you see an element, for instance, zirconium, right? Remember, I showed you that in our computations, we had all zirconium isotopes, including unstable, right? But when we execute this function, elemental abundance, it decays. It allows all unstable isotopes to decay into their corresponding stable isotope. Okay, so therefore you shouldn't care about this. It automatically decays them. Okay, yeah, and there are two curves here, as I promised. The black one corresponds to cycle 0, from which we started, and the orange one corresponds to cycle number 830. Of course, the difference between the cycles corresponds to the result of iProcess nucleosynthesis. So these initial abundances have been increased to these ones by neutron captures corresponding to second peak. Okay, now let's go further. Relative mass fractions. Please read this text later. I'm just going to execute the cells and comment on the plots. Okay, what's the difference between this plot and the previous one? In the previous one, we had just raw mass fractions, right? You can see the numbers of mass fractions, of course, they all below 1, 10 to the minus 6 of water, 10 to the minus 5 maximum for barium and xenon. In the second plot, as you can see here, the abundances logarithms are already like 10 to the 4, 10 to the 5. This is because here we plot mass fraction divided by the initial mass fraction x sub naught. And this is reflected here. We make a plot for cycle, PPN cycle, which is 830, but we divide all these mass fractions by mass fractions that correspond to cycle, reference cycle with number 0 here. If I put instead of 0 here, PPN cycle, guess what we will get? What will we get if I put instead of 0 the same PPN cycle to which we scale? What should I get? This is a question. I don't hear any answer. Oh, not surprisingly, I get 0. And this is 0 for logarithm, which means that the ratio of mass fraction is 1. Obviously, when I divide mass fractions by themselves, I get 1. So when I choose for reference cycle 0, then I just compare calculations with the initial abundances. Okay. Now let's continue. This is just checking where we are. Directory, what we have here. Okay. Now here in the next cell, I will make a similar plot, but instead of dividing calculated mass fractions by the initial one, we will divide them by the solar mass fraction.
Sorry, Pavel, I got a question.
Yes.
So when you showed the plot before, and when you chose the reference to be the PPN cycle itself, shouldn't the values scale around at 1 and not 0?
But this is logarithm. Logarithm of 1.
Oh, yeah. Okay. So it's basically subtracting and not dividing.
Yeah, you can. During next week, you can play with these notebooks just to get understanding, because of course it's difficult just to listen when someone explains. I just walk you through all these notebooks, but next week, please try them. Okay.
These are not solar scale, right?
These are not solar scale. This is a scaled relative to initial mass fractions. But in the next notebook, we are going to divide them by solar abundances, and the next cell will plot solar scaled.
Okay, thank you.
Okay, so now I'm going. Yeah, now you can see on the vertical axis, this is mass fraction x, again, decimal logarithm. Mass fraction x divided by x solar, okay? This is relative to solar. And you can check the difference relative to initial, it goes relative to initial to 10 to the 5, right? But relative to solar, it goes to 10 to the 2. This is just because the initial, they are subsolar, significantly subsolar for CMP I stars. They are 2 orders of magnitude subsolar. Okay, now let's go further. You will read all these comments because okay, now using the pinning method. First, let me just choose here again for our case. We will choose the range of proton numbers to plot. And now using an observational data file, okay? So for each of 3 I-process nucleotides cases, this cell will select the right star to compare, the right observed abundances. You shouldn't care about this in this notebook. Okay, let me just. Okay, so now these black circles with error bars, these are observed abundances for 1 star. I can tell you what the star is, our favorite star, CS 31060 minus 050, doesn't matter, because this is not research, this is educational notebook, okay? And you can see the orange curve for the second peak. This is what we've just calculated. These are predicted abundances. But of course, you can ask how well they fit the observational data. This is because we adjusted parameter. Adjusting parameter can be, it's actually like a shift, a vertical shift, right? And this vertical shift hides, this vertical shift is proportional to dilution coefficient that I mentioned before. But in this plot, we don't use dilution coefficient. Instead, we use the so-called pinning method. You can see here, which we select Z pin equal capital Z pin. And for capital Z pin, if we go back for our case, here, second peak, capital Z pin was 57. Let me go back to the plot. Okay. So this means that if I look at Z equal 57, yeah, this is Z equal 57, this one, lanthanum, okay? You can see that our predicted curve, orange curve, goes exactly through lanthanum, right? This is because lanthanum was chosen here as a pinning element, which means that we say, please move predicted lanthanum abundance vertically so that it goes directly through the observed lanthanum abundances, and then adjust all other predicted abundances by the corresponding shift, right? Okay, makes sense. So you can check this way. You can check that in principle, you can reproduce the observed abundances. So here we use this pinning method. We can choose for pinning element not lanthanum 57, but say samarium or whatever. It's up to you. Okay, let's go further. So now we are going to do some chi-squared test for a series of cycles. Remember, we have chosen actually 4 cycles around our preferable one, 830, to find the best fit. Okay. So you can see here it just displays our selected cycles: 800, 830, 860, and the last one 891. Okay. So this selection was done automatically for the corresponding case. Okay, now we make a plot. Let's wait. You see that this circle here is black. So usually not longer than 1 minute. You just have to be patient and wait 1 minute maximum. Yeah. Okay. So now you can see this plot still uses pinning method. Z small underscore pin is equal Z capital pin. Right. And as I explained you before, the pinning is done for lanthanum here, right? But unlike the previous plot, here we make 4 plots for the selected 4 different time steps. You can see here I use name time step or cycles, and you can see they will of course slightly differ because different cycles corresponds to different neutron exposures, right? And only one neutron exposure will be long enough. They will converge actually to the same solution as is already almost seen here. And now our task is to select the best cycle among these 4, or you can choose 10 cycles. Select the best one, and this will be, guess what, 830, as I promised, which will give the minimum chi-squared value, right? And chi-squared value is calculated, of course, by comparing predicted abundances with observed ones, including error bars taken into account. Okay. So now I'm going, yeah. And when this function was making this plot, it also calculated the corresponding chi-squared. You can see. So chi-squared was saved in this array, chi2i, for whatever number of cases we can see that here we have 4 cases, there's 4 cases, and now I just plot chi-squared calculated for 4 cases. You can see we have 4 cases, 0, 1, 2, 3. These are the corresponding cycles, time steps, 800, 830, 860, 891, and these are calculated chi-squared. You can see that the minimum chi-squared, this one 14.7, is for the cycle number 830. So therefore it was chosen at the beginning as the best fit cycle. But in principle, when you do research, you can use chi-squared method to find the best fit cycle among small number of neighboring cycles, right? Okay. Now here we can use manual pin. which means we still use the same pinning element, lanthanum, but we adjust, we say to what abundance it should pin. In this case, for instance, I want lanthanum for second peak. I want lanthanum abundance to be pinned at the value 2.10, okay, which I think is still the same, the observed abundance. So this is just demonstration of the manual pinning, okay. Oh no, this is not related to observed abundances anyway. So you can see this is lanthanum, our pinned element, and you can see that its abundance is if I put my cursor here, you see numbers. So y is equal approximately 2.10, 2.1, and this is the value that I used for pinning. I could, excuse me, I could say pin lanthanum abundance to 2.5 here. Then all the curve would move with lanthanum to 2.5, okay? So now next cell, we are almost done. Next cell just makes a plot of abundances using log epsilon. You know, log epsilon is one of the abundances used. We have mass fractions, we have square brackets, we have epsilon. So this is actually the ratio of the number density to the number density of hydrogen plus 12. Okay, this is just the standard definition of log eps. If we execute this cell, we will get, yeah, this is log epsilon abundance, right? And log epsilon abundance, of course, it's huge for helium, not for hydrogen, because this is I process occurs in the helium burning shell where there is almost no hydrogen. But all hydrogen, of course, is now in the form of helium, which is, you can see, close to 9. This is just log epsilon plot. And finally here, we are going to make the plot that I mentioned before with dilution coefficient applied. So in this plot, we actually mix predicted abundances. We take a small fraction of them, 0.25%, and mix them with initial abundances, trying to reproduce observational data. So, yeah. So you can see the orange curve. This is our calculations for the second peak that we've done. That corresponds to cycle that gives the minimum chi-squared cycle 830. And you can see how well it fits the observed abundances. Don't ask me about barium, because other stellar spectroscopies, even from the same group, they report lower barium abundances around 2.4. In which case it will nicely also fit the orange curve. Finally, we can make isotopic abundance plot, not elemental. Before we considered only elemental abundance. This is isotopic abundance plot, yeah. And you can see here there is an argument which called decade, and decade says decade wherever we have chosen for decades. It should be either true or false. Sorry for scrolling. Where we have selected the value for decades somewhere. I can print it out. Okay. So I can print it out. Decade. What it is? It's false. So this means that this plot is made. This plot includes undecayed isotopic abundances. Undecayed. So it includes unstable isotopes. If I change here, decayed is here false, right? If I change here decayed false to true and comment false, then it will make plot for decayed abundance, only for stable ones. This is for stable ones. It doesn't look any more that fun as before, right? This is for decayed abundances. If again for undecayed, decayed false, okay. Okay. This is more fun. Okay, I've just shown you these hidden research notebooks Okay, and I encourage you, I recommend you during next week to try to play with them. Please use so far only this iProcess notebooks. You can try the other ones, but I have not showed them to you yet, but they should be similar. So therefore it's up to you. So I'm going to stop sharing my screen. Do you have any questions about this plot, so that I will not stop sharing my screen?
Pavel, can you hear me? Hello.
Yeah, yeah.
So yeah, I have one question. This the decade parameter that we have put false in this particular plot. Can we do it for the previous plots as well? Can we keep the reductive nucleides alive for the previous plots also?
Yeah, you can check this how I showed you with this question mark, right?
Okay.
You see, this is a different function. The instance, the output data instance is still the same, PA. Then dot, and then the function. Here function is iso_abund. Okay, we can check, by the way, let's check this. Let's do this here instead of decade. Let me ask PA dot, what was its name again? Iso_abund, question, right? Okay, here it gives the list of arguments, yeah, and their default values. Okay, you don't have to put all arguments because they already have some default values. If you are okay with default values, just you don't change them. Okay, now decade default is false, right? So I don't even have to say hey, here explicitly decay false because it's default value, right? Okay, now let's go to other function that I showed you before, right? Let me go here. Not, a second. It was in the other notebook, I think, right? Okay, but we can do this. This is elemental abund, right? PA elemental abund. Let's go down and sorry, elemental abund. So we change here the name, elemental abund. Elemental abund code. Okay. Oh, right. Yeah, and I know the answer to your question. You see, when we ask what elemental abundance says, it plots already decayed elemental abundance because it plots elemental abundances, right? Therefore, by default, it plots them decayed, right?
Okay, yeah, that was my concern. So
yeah, because it plots elemental abundances, yeah.
Yeah, but from the output files, maybe we can get it.
Because unstable isotopes, you plot them only when you are interested in isotopic abundances, right? But elemental, by default, it says plots decayed elemental abundances. So it uses actually this parameter decayed equal true somewhere inside the function. It's hidden, okay. But this is its point. You plot elemental abundances, they should be decayed, right?
Yeah, okay.
This is what you observe in a real star. In the CMP star, you see a mixture of initial chemical composition with decayed elemental abundances. Okay. I'm going to stop sharing my screen, and if you still have,
I have one more question actually.
Yeah.
So, is it like always the last time sections are only important, like 830 or something like that, or like we need to sometimes calculate the intermediate time steps as well? Or
yeah, good question. You see, you usually do your calculations beyond time steps that you expect to be interested in, right? Beyond this time step. So that the time step you will actually need will be included in your calculations, computations. And then you do analysis of your results by comparing, say, predicted abundances with observed ones, or using some other methods. And then you select the preferred time step, right? Like I showed you. So in this case, I selected time step 830, which is below the final one, 891, because it provides me the minimum chi-squared when I compare predicted abundances with observed ones with this star. Maybe for other star, if I use the other star, I should select a slightly different time step, which is actually the fact.
Okay, so maybe I can find this information also in the publications that.
Yeah, you should
okay.
have a look at the publications. They explain in more details technical and scientific things. Okay.
Okay, thanks a lot. I check them out.
Okay. Any more questions? If there are no questions, I'm going to stop recording and say you bye-bye. See you next Friday. And please try, no, please, it's up to you, but I would encourage you to try to use this TINA things, okay? TINA computational tools. Okay, bye-bye.
Thank you, Pavel. Bye.
You're welcome. Bye-bye.
Bye-bye.
Thanks,
Thank
Pavel.
you.
Bye-bye.
Bye-bye, guys.